So we have question number 10.6. The question says a beam of light consisting of two wavelengths, 650 nanometer and 520 nanometer, is used to obtain interference fringes in a Young's double slit experiment. Find a distance of third bright fringe. Third bright fringe you have to find on the screen from the central maximum of wavelength 650 nanometer, right? So when we are using the wavelength of 650 nanometer, what is the distance from the central maximum of the third bright fringe? So simple, the formula we know that xn is equal to n lambda d by d for bright fringes, right? So we have to use this formula, position of bright fringe, that is the general formula for this. And after that, using this, we have to solve the first question, that is distance of the third bright fringe from the for lambda is equal to 650 nanometer, right? So xn is equal to n lambda d by d, and that is given as n is equal to 3, lambda is equal to 650 into 10 to the minus 9 meter, right? And substituting the value that we get is x3 is equal to 3 into 650 into 10 to the minus d by small d. And here the capital D and a small d is not given in NCERT, particularly the PDF I have, latest PDF. So I am leaving it that way. If in the previous book or previous edition the value is given, you can put that value here for capital D and a small d. Capital D is basically the distance between the cardboards, and small d is the distance between the two slit, right? So you can put that here, and you can get that this is the central maxima, and particularly this maybe you can say that there are so many bright fringes that is going to be emerged, but we are talking about third bright fringe, right? So this is a third bright, and the distance between this is your y or xn, you can say, right? So this is the thing, you have to put the value d or d not, that is not given in the case particularly, so I haven't put that. Now B, least distance where bright fringe of both wavelength coincide. So if we are taking the lambda of 650 nanometer, and we are taking again in the second case the lambda of 520 nanometer, so a place where this both bright fringe, for this both case the bright fringe going to coincide, we have to talk about that situation, right? So we can say that by the same formula, that the general formula we are using, xn is equal to n lambda d by d, that we have. So suppose for this case, we that particular bright fringe is going to coincide at x into the n1, right? xn1, okay. So we have to take the value of n1. Lambda is your 650, and d is going to be constant, and for this case that is going to be considered, let's assume x n2, and that is we have to put the value for n2, and lambda, that is in this case the lambda 2 520 nanometer, d by a small d is going to be same. Now we have to, this two distance is going to be same, right? Because that is coinciding, the two wavelength is coinciding, that bright fringes of two wavelength is coinciding, means they have same length from central maxima, right? So xn1 is equal to xn2, okay. So xn1 is equal to xn2, that means n1 lambda 1 d by d is equal to n2 lambda 2 d by d. So d going to be cancel out, and n1 lambda 1 is equal to n2 lambda 2. So now you can see that how I have deduces that value that is written here, and now you can put the value directly, and you can get the condition, that is 5n1 is equal to 4n2, means n1 is going to be 4 and n2 is going to be 5 by comparing. And you can put any value for this, you can put like you can either get the value of n1, or you can calculate the value of n2, both will same, so it will give the distance, same distance. So I have calculated here x n1, and that is n1 lambda 1 d by d, that is 4 into 650 into 10 to the minus 9 d by d. and that particularly because the d and small d is not given, so I have written in general form. As I have told earlier that if in the previous editions the value is given, you can put that and you can get to the result. Okay.